We come now to the last big theorem of the course, which is the divergence theorem. It says the following. So let E be a solid region in R3. And we should assume that it's bounded, it doesn't go off to infinity. Now this has a boundary surface, we'll call it S. So let S be the boundary surface of E. And let's give it the outward orientation. So here's our solid region E. Here's the boundary surface S. Then we choose the normal vector that orients S to be the unit normal vector that points out of the region like that. Okay. And let F be a differentiable vector field defined on all of E. Then what the divergence theorem says is that the double integral over the boundary surface S of f dot ds is equal to the triple integral over the solid region E of the divergence of f with respect to volume. So this formula actually is pretty intuitive. I think it's more intuitive than Stokes' theorem. Why is that? So what is this saying? So remember that the left-hand side here, this measures the flux of F out of S. So it measures the extent to which the vector field F, say this is the vector field F, is pointing out of the region E along its boundary. So these arrows that I'm drawing here, these would all give you positive contributions to the outward flux. Maybe at some points the vector field is pointing in towards E, and those parts of the boundary would give you negative contributions to the outward flux. Okay, and then divergence, what is this? Well, this is positive where F is expanding, or sort of decompressing, or diverging if you like. So the vector field looks like this. The divergence is positive, and it's negative where F is sort of contracting or getting compressed or doing the opposite of diverging, where it looks like this. Okay? So what the theorem is saying is that if we take the sort of local measure of how much the vector field is expanding and add that up, or more precisely integrate it over the entire solid region E, then we get the net flux out of the region. So if you think of F as the velocity vector of a fluid, if this fluid is spreading out, then some fluid is going to have to escape the region to make room for the fluid inside the region to spread out. On the other hand, if fluid is flowing into the region, then it's going to get more compressed in the region. You have experience with this in everyday life. Let me just draw a couple of pictures here. So here's an elevator. Here's shown from the top. Okay, so you've got some people in an elevator. I'll draw these as dots. And people tend to spread out, so they're not invading each other's personal space any more than necessary. And let's say a bunch of people get on the elevator. Okay, so now there's a flux through the elevator door into the elevator, and the people in the elevator are going to have to get closer together. So now I lost count. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now people are coming into the elevator, and the people in the elevator are squeezing closer together. So this is where the outward flux is negative because there's an inward flux. So the outward flux is negative. And inside, since people are getting closer together, the total divergence, the integral divergence, is also negative. And if later the elevator stops at another floor and a bunch of people get out, then everybody will spread out as much as they can. And so there will be a positive outward flux and a positive divergence, or positive total divergence, inside the elevator. So that's just to give you some intuitive idea. Let's do a really simple example. Suppose that F is the curl of some other vector field G. So what does the divergence theorem say in this case? The divergence theorem says that the double integral over S of the curl of G dot ds is equal to the triple integral over E of the divergence of the curl of G with respect to volume. And in fact, this equation says that 0 equals 0. Why is that? Well, let's look at the right side first. We saw before that if you take any vector field and take its curl and then take its divergence, then you get 0. So this is the function 0. When you integrate that over anything, you get 0. Now what about this? Well, the curl of G doesn't have to be 0, but the total integral of the curl of G over S is 0 by Stokes' theorem. Why is that? Well, what Stokes' theorem really tells you is that the double integral over S of the curl of G dot ds is equal to the line integral of the curl of G around the boundary of S. But S has no boundary, so if you take a solid region and take the boundary of the solid region, that surface has no boundary. If you like, you could think of it like this. So here's the surface S, and it has no boundary. Well, if you want to give it a boundary, we could cut out a little ball. And then the double integral over S of the curl of G dot ds is the limit. Let's give this the size of this ball names. This is a ball of size epsilon, or a disk of size epsilon that we're cutting out. So it's the limit as epsilon goes to 0 of the double integral of S with a disk of radius epsilon removed. Of curl G dot ds. And by Stokes' theorem, this is the limit as epsilon goes to 0 of the line integral over the boundary curve. So this little disk has a boundary curve C. Let's just write boundary of S. And it'll have sort of a funny orientation as the boundary of, sorry, this is not the boundary of S, it's the boundary of the disk of radius epsilon. And it'll have a funny orientation because it has to be oriented as the boundary of the rest of S. So it's going to be oriented going clockwise, like that, of G dot dr. But if you take the same vector field and integrate it over smaller and smaller curves, in the limit you're going to get 0. Okay? So that's just a basic example to show you what the divergence theorem is saying. In the next lecture segment, I'll show you how you can use the divergence to do calculations.